So we have one more video that's part of our exponential function section. Really is a big part of the course, so that I intentionally wanted to spend quite a bit of time working through these different parts of 6.1 and 6.2. And this last video is all about one thing called the natural exponential function, which is a very particular function, a very special function in mathematics. And so let's start figuring out what this thing is. And we're going to start out by looking at this expression 1 plus 1 over n to the n. And we're going to plug in larger and larger values of n and see what happens. Now, we're raising it to the nth power, so when you raise something to the 1,000th power, millionth power, you would expect this to be big, right? We're putting a really large exponent in there. You would expect to see something really, really large. And I don't want to write all the calculations out on my main sheet, so I'm going to do some of this on a separate sheet of paper. So if n is equal to 1, 1 plus 1 over n to the n is just 1 plus 1 over 1 to the 1, which is 1 plus 1 to the 1, which is 2 to the 1, which is 2. So when n is equal to 1, we get 2. When n is equal to, I guess I want to check 2 next, 1 plus a half to the second power is going to be 1 plus a half is 3 halves to the second. When I square that, I get 9 fourths. 9 fourths I'm going to write as a decimal, 2.25. So when I plug in n equals 2, I get 2.25. Okay. And n equals 3. 1 plus 1 over 3 to the third. So I put 3 in both positions for n in the original formula. I get 4 thirds to the third power. And that's like 4 to the third over 3 to the third. That's 64 27ths, which is about 2.37. So I think you see the point of what I'm doing here. I might not work through every one of these. N equals 4. 1 plus 1 fourth to the fourth is 1 1/4, or 5 fourths to the fourth. That's going to be about 2.44. So these are getting larger, but they're not getting that much larger. When I plug in 5 and do 1 plus 1 over 5 to the 5th power, I get 6 fifths to the 5th, which is about 2.49. When I plug in 10 and I get 1 plus 1 over 10 to the 10th power, I get 2.59. I think one more of these I just want to write out. And if I plug in n equals 100, 1 plus 1 over 100 to the 100th power, so that's going to be 100 100ths plus 1 100th is 101 100ths to the 100th power. So we're raising a number to the 100th power. And it's kind of surprising that this just comes out to be about 2.70. Doesn't come out to be large. And if we put 1,000, we get about 2.717. If we put in 1,000,000, raise that to the millionth power, we get about 2.71828. What's happening is, as n gets larger and larger, one plus 1 over n to the nth power doesn't get larger and larger, but it approaches a particular number that is denoted with the letter E. The E, I think, comes from the first letter of the name of a very famous mathematician, E-U-L-E-R. We pronounce Euler. E is approximately 2.71828. And E actually has an infinite, non-repeating decimal expansion. So it's impossible to write down exactly what E is. It's kind of like the number pi. If you've ever heard of people who talk about decimal places of pi, pi's decimals go on and on forever. And there's no pattern, there's no repetition. It's a very special kind of number. So E is also a special kind of number. And E is about, just, you don't have to know the decimal, but it's about 2.7, very close to 2.7. And so what we've seen is, as n approaches infinity, 1 plus 1 over n to the n doesn't get larger and larger. It approaches E, this number that's about 2.71828, and whose decimal goes on and on forever. So in math, we really like this number E, and it turns out to be very important in calculus, and we can't see why yet, but when you take calculus, you'll find out why. And so we can use E as the base of an exponential function. So just like we say f of x equals 2 to the x, we can say f of x equals e to the x is called the natural exponential function. So don't think of e as like a variable or as a unknown, like a x or a y or a z. It's a number like pi, it's a constant. E to the x is like 2 to the x or 5 to the x. You know, it's approximately 2.7 to the x power when we write e to the x down. So it's a constant to the x power. Why we use the word natural, what doesn't seem very natural at all in a pre-calculus class, it seems like the weirdest thing you could ever want. And it turns out in calculus that it has some very special properties, and we like them a lot. So right now, we just want you to be comfortable with e being a constant, and we want you to see this function. So we're going to move to another page here. So exercise, graph f of x equals e to the x. So we're going to do a rough sketch just like we do with our other exponential functions. What you want to note is that the base b is greater than 1, since e is about 2.7, right? so we can draw a rough sketch of this graph, just knowing that the base e is greater than 1. We know it's got to have this kind of shape. We know its y-intercept is 0, 1. E to the 0 is 1, just like that would be true for any number. Maybe call that number 1. Let's call number 2 graph f of x equals e to the minus x. What we notice is we've replaced x with minus x inside the exponent of the function. So this is going to be a reflection through, we haven't seen too many of these, but through the y-axis. We reflect through the x-axis when we have a minus sign in front. When we have a minus sign inside the function like that, we reflect through the y-axis. So you also know how to graph the function f of x equals e to the minus x. It's going to have a shape like this. They both have the x-axis as a horizontal asymptote, but in different ways, right? Here it's at minus infinity for e to the x, where the graph approaches the x-axis. For e to the minus x, it's off at plus infinity, where the graph approaches the x-axis. Still has 0, 1 as a y-intercept. And really, that right now, it's this graphing that is our main interest. Just getting used to thinking of e as an actual number, and e to the x is a function we can graph. So let's do another one. F of x equals 1 minus e to the minus x. Okay, so what do we got going on here? Well, we got our reflection through the y-axis. We could think of this as minus e to the, oops, I forgot my minus, minus e to the minus x plus 1. So we also have a reflection through the x-axis, both of them here, and we have a vertical shift. So I would say we have 3 transformations going on of up 1 unit. So maybe I'm going to draw a couple of preliminary graphs. We already have our e to the minus x, so let me put this here. I'm just going to recopy that e to the minus x. And then what would minus e to the minus x be? Well, we're going to take this graph as is here, and we're going to reflect through the x-axis. So this is now a picture of y equals minus e to the minus x. And now I just got to shift up 1 unit, so I'm ready for my final. If I can do that a little neater. When I do the vertical shift, the horizontal asymptote moves, so I got to indicate that. That's y equals 1. Let's see, my, now it's not so obvious where the y-intercept, well, I guess it isn't hard to see where the y-intercept ends up. That's 0, 1 there. This is 0, negative 1, right, when we reflect. So when we shift up 1 unit, we should have our y-intercept right at 0, 0. And if you plug in if you plug in x equals 0, you get 1 minus e to the 0. 1 minus 1 is 0. So the graph does something like so, approaching that line y equals 1 as x goes off to infinity. So there's our final sketch of 1 minus e to the minus x. Okay, one more I wanted to do with you is f of x equals e to the x minus 1. That's a horizontal shift only to the right by 1 unit. And let's just go back to our original e to the x graph that we're working from here with no transformations. And we just want to shift that guy to the right by 1 unit. When you do the horizontal shift of an exponential function, the look doesn't change that much. The asymptote stays in the same place. You still approach the asymptote at negative infinity. You're still going to go around this corner and go taking off to infinity as you move to the right. The y-intercept, though, is no longer 0, 1. So right here on the e to the x graph, the y-intercept is 0, 1. But that point has shifted over 1 unit. This new y-intercept we can get by plugging in e to the 0 minus 1. That's e to the minus 1. And so this point is 0, e to the minus 1. And I'm just thinking, let's just pull up a value. What is e to the minus 1? E to the minus 1 is about 0.368. I just checked on my calculator. So that's actually got a decimal value. It's just 1. It's approximately 1 over 2.7. It's okay to label the graph either with the decimal or with the 0 comma e to the minus 1. And that's it. That's the end of our talk about the natural exponential function. And actually, this is the end of the videos that deal with 6.1 and 6.2, our introduction to exponential functions.